Overview study on USB on-the-go device ISP1761 by ST-NXP Wireless. Welcome to the training module on USB on-the-go device ISP1761. Today's outline consists of the features, applications and connection diagrams, internal block diagram, hub, clock, power supply connection and interrupt, and endpoint description, on-the-go state diagram. The ISP1761 is a single-chip, high-speed universal serial bus on-the-go controller integrated with advanced ST-NXP wireless slave host controller and the ST-NXP wireless ISP1582 peripheral controller. The high-speed USB host controller and peripheral controller comply to Universal Serial Bus Specification Revision 2.0 and support data transfer speeds of up to 480 megabits per second. The enhanced host controller interface core implemented in the host controller is adapted from Enhanced Host Controller Interface Specifications for Universal Serial Bus Revision 1.0. The on-the-go controller adheres to the on-the-go supplemented to the USB specification Revision 1.3. The ISP1761 has 3 USB ports. Port 1 can be configured to function as a downstream port, an upstream port, or an on-the-go port. Ports 2 and 3 are always configured as downstream ports. The on-the-go port can switch its role from host to peripheral and peripheral to host. The on-the-go port can become a host through the host negotiation protocol as specified on the on-the-go supplement. Some of the on-the-go and peripheral controller specific features include on-the-go transceiver, fully integrated, HNP, status and control registers for software implementation, programmable timers with high resolution for HNP and SRP, high-performance USB peripheral controller with integrated serial interface engine, first in first out memory and transceiver. The ISP1761 can be used to implement a dual-row USB device in any application, USB host, or USB peripheral depending on the cable connection. If the dual-row device is connected to a typical USB peripheral, it behaves like a typical USB host. The dual-row device can also be connected to a PC or any other USB host and behave like a typical USB peripheral. Here's a typical internal connection diagram of the device ISP1761. It has a generic processor interface block, which has memory management unit slave DMA controller, interrupt controller, hardware configuration registers, transaction translator, and RAM, which is interconnected to USB full-speed high-speed data path. It has 3 USB ATX blocks, EHCI and operational register block, PD, and payload memory block. The EHCI block and the high-speed USB hub block are the main components of the advanced ST-NXP wireless slave host controller. The internal high-speed USB hub block replaces the companion host controller block used in the original architecture of peripheral component interconnect, high-speed USB host controllers to handle full-speed and low-speed modes. The hardware architecture in the ISP1761 is simplified to help reduce cost and development time by eliminating the additional work involved in implementing the OHCI software required to support full speed and low speed modes. The ISP1761 implements an EHCI that has an internal port, the root hub port, which is not available externally, on which the internal hub is connected. The 3 external ports are always routed to the internal hub. The ISP1761 implements an EHCI that has an internal port, the root hub port, on which the internal hub is connected. The 3 external ports are always routed to the internal hub. The internal hub is a high-speed USB hub including the TT. The ISP1761 has 3 ports. Port 2 does not need to be enabled using software if only port 1 or port 3 are used. No port needs to be disabled by external pull-up resistors if not used. The DP and DM of the unused ports need not to be externally pulled high because there are internal pull-down resistors on each port that are enabled by default. All the interrupt events are represented by the respective bits allocated in the HCI interrupt register. There is no mechanism to show the order or the moment occurrence of an interrupt. The asserted bits in the HCI interrupt register can be cleared by writing back the same value to the HCI interrupt register. This means that writing logic 1 to each of the set bits will reset the corresponding bits to the initial inactive state. Here's a diagram of the phase locked loop clock multiplier which is present inside the device. The internal PLL requires a 12 MHz input, which can be a 12 MHz crystal or a 12 MHz clock already existing in the system with a precision better than 50 ppm. This allows the use of a low-cost 12 MHz crystal that also minimizes electromagnetic interference. When an external crystal is used, make sure that the CLKIN pin is connected to VCC. The PLL block generates all the main internal clocks required for normal functionality of various blocks: 30 MHz, 48 MHz, and 60 MHz. This slide shows a typical power supply connection to ISP1761. A 4.7 microfarad to 10 microfarad electrolytic or tantalum capacitor is required on any of the pins 5, 50, or 118. All the electrolytic or tantalum capacitors must be of low ESR type. In hybrid mode, VCC can be switched off using an external PMOS transistor controlled using one of the GPIO pins of the processor. This helps to reduce the suspend current, ICC, below 100 milliamps. If the ISP1761 is used in hybrid mode and VCC is off during suspend, a 2 millisecond reset pulse is required when power is switched back on before the resume programming sequence starts. ISP1761 has overcurrent detection built inside. The range of the overcurrent detection voltage for the ISP1761 is 45 millivolts to 100 millivolts. The port power will automatically be disabled by the ISP1761 on an overcurrent event occurrence by deasserting the PSWN signal without any software intervention. The digital overcurrent scheme requires using an external power switch with integrated overcurrent detection, such as LM3526, MIC2526, or LM3544. These devices are controlled by PSWN signals corresponding to each port. When VCC is directly connected to the reset end pin, the internal POR pulse width and TPORP will typically be 800 nanoseconds. The pulse is started when VCC rises above VTR-IP of 1.2 volts. The recommended reset input pulse length at power on must be at least 2 milliseconds to ensure that the internal clocks are stable. The reset end pin can be either connected to VCC using the internal POR circuit or externally controlled by the microcontroller or ASIC. The internal addressable host controller buffer memory is 63 kilobytes. The ISP1761 is a slave host controller. This means that it does not need access to the local bus of the system to transfer data from the system memory to the ISP1761 internal memory. Therefore, correct data must be transferred to both the proprietary transfer descriptor and the payload area by PIO or program DMA. The RAM is structured in blocks of proprietary transfer descriptor and payloads so that while the USB is executing on an active transfer-based proprietary transfer descriptor, the processor can simultaneously fill up another block area in the RAM. A proprietary transfer descriptor and its payload can then be updated on the fly without stopping or delaying any other bus transaction or corrupting the RAM data. The on-the-go state machine is implemented with software. The inputs to the state machine come from 4 sources: hardware signals from the USB bus, software signals from the application program, internal variables with the state machines, and timers. The on-the-go state machine is the software behind all the on-the-go functionality. It is implemented in the microprocessor system that is connected to the ISP1761. The ISP1761 provides registers for all input status, the output control, and timers to fully support the state machine transitions. The registers involved in this operation are on-the-go control register, on-the-go status register, on-the-go interrupt latch register, on-the-go interrupt enable fall, on-the-go interrupt enable rise, and on-the-go time register. Each USB peripheral is logically composed of several independent endpoints. An endpoint acts as a terminus of communication flow between the USB host and the USB peripheral. An endpoint is assigned a unique address or identifier before any transfer of data is established. An endpoint can be of interrupt type, asynchronous type, or bulk type depending on the type of data transfer required.